Alright, let's take a look at the solutions for 5.3, linear programming problems. First problem is to maximize z is equal to 40x plus 12y, subject to the following constraints: 6x minus 2y less than or equal to 12, 3x plus y less than or equal to 9, and both x and y greater than or equal to 0. Look at the completed graph with the closed feasible region shaded. If we look further down, we see that the corner points of 0, 9, 2, 0, 0, 0, and 5 halves and 3 halves have been identified. That, being plugged into the objective equation, yields the following results: that 0, 9 yields 108, 2, 0 yields 80, 0, 0 yields 0, and 5 halves and 3 halves yields 118. Therefore, we see that the value of 118 is the maximum value, and that occurs at the corner point of 5 halves and 3 halves. Next example. Minimize z equals 130 plus 120y, subject to the following constraints: 1/2 x minus y greater than or equal to 2, x plus y is greater than or equal to 7, and both x and y greater than or equal to 0. Notice that after you're done graphing this, that we have an open solution region. This is only a two-corner region, so therefore identifying the two corners 7, 0 and 6, 1 and substituting them into the objective equation yields the results of 910 and 900 respectively. Therefore, the minimum value of 900 at the corner point of 6, 1 is a solution to the linear programming problem. Let's take a look at an applied problem, the dietitian problem. Number 3. The dietitian needs to plan a diet for a patient using a combination of different foods. Each container of food A contains 1 unit of additive 1 and 1 unit of additive 2, and each container of food B contains 1 unit of additive 1 and 2 units of additive 2. The patient needs at least, and notice that the words at least are important there, 5 units of additive 1 and at least 6 units of additive 2. How many containers of each food should the dietitian use in order to meet the patient's needs and minimize the cost? The cost of each food, that is food A, costs $3, and each container of food B costs $5. We'll let X and Y represent food A and let Y represent food B. Using the above information will yield the following set of equations. So we have the minimizing equation of 3x plus 5y, and it's subject to the following constraints: that x plus y is greater than or equal to 5, x plus 2y is greater than or equal to 6, and both x and y greater than or equal to 0. Notice the open solution region. Identifying the corners, which there are only 3, 0, 5, 6, 0, and 4, 1. Each of those are tested into the objective equation, yielding the results of 25, 18, and 17 respectively. Therefore, the minimum cost will in fact be $17 when 4 containers of food A and 1 container of food B is used. Next problem. Ginny knits 2 different types of capes. The Ginny model, which requires 3 hours of knitting and 7 hours of embellishing, and the Helen model, which requires 5 hours of knitting and 5 hours of embellishing. Ginny has at most 60 hours to knit and at most 100 hours to embellish the capes. How many of each cape should be made in order to maximize her profit? if she yields a profit of $80 from each Ginny cape and $100 from each Helen cape. Setting up our system with the objective equation of z equals 80x plus 100y. See the graph, see the closed solution region, shaded, and notice that the corners of 0, 12, 14.3, and 0, 0, 0, and 10, 6 have been identified as the four corners to this closed solution region. When each of the corners are substituted into the objective equation, notice that it yields 1200, 1144, $0, and $1,400. Therefore, the choice of $1,400, which will be the maximum profit, is yielded when 10 Ginny models and 6 Helen models are produced. Problem 5. The top two dolls that a toy manufacturer makes are called the Baby Wiggles and the Sleepy Baby. To make a case of Baby Wiggles requires 5 units of raw material in 1 unit of time. A case of Sleepy Baby takes 3 units of raw materials and 2 units of time. On a given day, the manufacturer has at most 150 units of raw material and at most 44 units of time. If the manufacturer makes a profit of $120 on each Baby Wiggles and $100 profit on each case of Sleepy Baby, how many of each should the manufacturer produce in order to maximize the profit? Once again, we're going to identify our variables. Let X represent number of cases of Baby Wiggles and Y number of cases of Sleepy Baby. Our profit equation is 120x plus 100y. That becomes our objective here, subject to the constraints of 5x plus 3y less than or equal to 150, x plus 2y less than or equal to 44, and both x and y greater than or equal to 0. See the graph, the closed solution region, and the corners identified 0, 22, 30, 0, 0, 0, and 24, 10. When those corners are substituted into the objective equation, they yield 2200, 3600, $0, and 3880. Therefore, the easy choice here again is that a maximum profit of $3,880 will be made when the manufacturer produces 24 cases of Baby Wiggles and 10 cases of Sleepy Baby.